So Beyond Infinite Plane said some stupid shit, and it's easy enough to disprove using a vector software. I'm using vector software instead of something like Photoshop because points are a little bit nicer for scale since they play nicely with decimals. So I've got my circle here that's representing the Earth. It's currently 39,590 points across, which is essentially, to give you my scale, I took the diameter of the Earth, multiplied it by 10, and then I divided it by 2 because I've got limitations on the size of the canvas. So right now we're looking at, for every 5 points, you have 1 mile. Okay, now that we've got that settled, let's go ahead and click on this red rectangle right here. This rectangle, you can see it says 0 points. It's actually 0.005 points tall. And that's because it is exactly to scale the height of a 6-foot observer. And notice how I've got him at 12 o'clock here on the sphere. Not at 11 o'clock, not at 1 o'clock, 12 o'clock. So there's our 6-foot tall human. And I'm just going to go ahead and zoom out, show you. Wow, look, you can kind of see him. He's still a little red dot there. Keep zooming out, keep zooming out. Wow, look at how flat the Earth looks around him. We know it's a circle. I just zoomed in on it. Funny how flat it looks, right? And in fact, I've got this curve right here. It's way thicker because otherwise I can't get my point across quite as well. Notice how flat it looks. Wow. In fact, it's only just now that you're starting to see that the line is no longer perfectly flush with the circle. Guess how long this line is? 155 points divided by 5, roughly 30 miles. 30 miles and you can barely see any curvature. And I can just keep going and keep going. It's going to keep looking flat. You can start noticing a little bit of curvature. But that sure as heck is like what? Now we're looking at 150 miles or so, still barely seeing a curve. Oh, I better drop it below the center of the frame, otherwise the lens distortion might make it look like it's getting curved. Oh wait, that has nothing to do with it because it's a circle. And if I zoom back in, I've actually got this little triangle right here. This triangle right here, this is Mount Everest to scale at 5.5 miles tall. And that would be assuming that we're going directly from sea level straight up a cliff to the height of 5.5 miles. That is the elevation of the peak of Mount Everest, the tallest thing that we are able to experience above sea level. Notice how I've got the observer at 12 o'clock here, and then I've got Mount Everest here, which is like what, 2 or 3 minutes on a clock. So we're not dealing with 11 o'clock and 1 o'clock. We're dealing with 12 o'clock and like 2 or 3 minutes. But if I draw a line between those 2 points, between the eye level of the observer and Mount Everest, notice how immediately the curvature gets in the way and you can't see it. Funny that, huh? In fact, if I hide that curve and I go to this curve right here, wow, I can't even see. And I keep saying curve. It's technically a line, but it's called a curve because it's a vector software. It's a line because it's only 2 points. Funny how those 2 points right here, these 2 points represent the accepted distance to the horizon from a human viewer of 6-foot elevation to what we consider to be the horizon distance at 6 feet, which is 3 miles. Look at how short that is. I mean, obviously, it's still really big compared to our observer. He's way down here. Look at him. But it's pretty short compared to the scale that we've got going on. But wait a minute. Can't we see boats way past the 3-mile mark of our horizon? Yes, we can. Guess why? Because if you look at this rectangle over here, in fact, I've got a curve, not that one, this one, that goes straight to that boat. But notice how when it's at the bottom of the boat, it intersects with the curvature of the Earth. Only by a little bit, but just enough that it would obscure part of the boat, right? Because boats disappear from the bottom up. But if I was to take this line and move it so that it's going to the top of the box. Now keep in mind, this box that I have representing a boat is close to, not exactly, but close to 100 miles tall, 0.1 on the scale. Notice how then we're able to see it over the curvature, but we can't see the bottom of it. Funny. It's almost like that matches exactly what we see in real life. And obviously I'm not taking perfect measurements of perspective calculations and haze and refraction and everything else. But generally speaking, on a curved Earth surface, you would not be able to see things from the bottom as they get farther and farther away. You would be able to see the top of them for a much longer distance, and that's because of how gradual the curvature of the Earth is, and because of, obviously, the height of the object and how much it's able to be above that curvature or below it. But once again, if we go from 12 o'clock to 2 minutes, Mount Everest is suddenly hidden. And now let's go ahead and compare that to, I've got a flat Earth right here. And on this flat Earth, I've got our 6-foot viewer right here. You can see that big old line right there. This 6-foot viewer is like, what, within 5 miles from the base of Mount Everest. Mount Everest, once again, just clicking on this so that I can verify all of the information. This Mount Everest has a height of 30 points, which is 5.5 miles, to the elevation from sea level. This black line is going from the viewer to the sun based on the flat Earth estimate of 6,000 miles, which is way up here. So you can see if I grab that line, it's going from the observer to the sun, 6,000 miles up. Notice how far away the sun is horizontally from the viewer, but it's still above Mount Everest. You would still be able to see the sun. Let's go ahead and just kind of skew the perspective here a whole bunch. I'm going to go ahead and move the sun just like way off the canvas here. Let's go ahead and just move it way over here parallel to where we had it before. And then I'm going to go ahead and take our line. I'm going to make that so that it goes straight to the sun again. And then let's go ahead and just make another line here so that we can get the horizontal distance from the viewer right there to the bottom of the sun right there. So we've got 64,000 miles, which is what, roughly 13,000 miles. The sun is 6,000 miles up. And I did that using this rectangle here. So this rectangle is 30,000 points, 6,000 miles. So the sun is 6,000 miles up. And what is that? Roughly 13,000 miles away. And if I grab this curve again that goes directly to the sun and I zoom back in on our scale model, notice how it's just barely setting over the peak of Mount Everest, which, keep in mind, is just 1 point. So it wouldn't even obscure the entire thing unless you're standing directly, what would that be? Directly west of Mount Everest. So it is an absolute given that to scale, the globe Earth matches what we are able to experience way more than the flat Earth model. Period. End of statement.